Thank you, and thank you for the opportunity. So I'm switching here a little bit gear now, and I give you the idea is to give you a quick overview about the Danish telescope and the current status of it and how we are getting ready for LSST on it. LSST, so the Danish telescope is shown here. So it's one of the smaller telescopes on the amazing observing site of La Silla and not the graveyard. And of course, obviously, the telescope is not a new telescope. So it's actually already about 45 years ago when it saw first light, which is approximately the same time when I also saw first light. So it's good to remember. And it has a primary mirror of 1.54 meter, which is also defining a bit the name here. It's a classical Ritchie-Carter optical system with a focal length of 13 meter, and it's on an equatorial mount. It is owned by the Upper University of Copenhagen, and it is at this point it is jointly operated by the Niels Bohr Institute, which is an institute of the University of Copenhagen, obviously, and the Undertaken, I hope I can pronounce that correctly. I'm sorry for that. Observatory in Czech Republic, with of course on-site support from ESO that provides electricity, internet, and some maintenance. Just very briefly, the Danish right now has two instruments mounted. The main instrument is the Danish faint object spectrograph and camera, or also called DFOSC. You maybe recognize, so it's part of the FOSC family, with like a similar instrument as the EFOSC at the NTT or the IFOSC at the Nordic Optical Telescope. It's a focal reducer type camera, which consists of a collimator and a camera. And between the telescope and the instrument, there is a filter and a shutter unit, or FASU, that has two wheels where you have a large variety of different kinds of filters. It used to have an aperture wheel, which was mounted at the focus of the telescope, and it includes the slits for spectroscopy, but that was decommissioned already in 2003. So since then, the telescope actually operated mostly as a photometric telescope. The second instrument that is there is a two-color lucky imaging camera, which is based on an electron multiplying CCD detectors and with a high frame rate of 10 hertz. So, of course, over the years, the telescope has had several refurbishments and upgrades. One of the major ones was in 2012. That was funded by the Academy of Science of the Czech Republic, and partly to a large fraction, let's put it that way, for a project also to study for the studies of near-Earth asteroid objects, and with a PI of Peter Pavich. So the main refurbishment here was to have a completely renewed telescope control system that was built by a Czech company, Project Soft, and that actually contains the main core is based on industrial hardware and components and solutions, which are working extremely stable. So there are several backups as well, and a fail-safe system. There is also a safety system to protect the telescope and the dome for example, intruders and entering the dome eventually, or bad weather, or also loss of a connection of the remote observer. So that means that the telescope is at this point, it can be used it can be fully remote controlled. It's not robotic. One of the things also what ESO has to provide is to refill the cooling system with liquid nitrogen per night. So that can only a human do. You cannot do that by a computer. And also since 2012, so the observing time is now shared in a half-half between the Danish astronomers and the Czech astronomers. On the Danish side, one of the driving science programs are included in the MINDSTEP collaboration with the microlensing network for the detection of small terrestrial exoplanets, with the aim to characterize extrasolar planets in the galaxy using the microlensing techniques. There are some other projects also, and I'm just showing here very briefly two examples, where one is the lucky imaging camera has been extremely useful in the event of a stellar occultation by the asteroid Chariklo, where with the Danish, can I see that now? With only the Danish telescope, it was actually possible to resolve the side events, which lasted only for about 0.1 or 0.3 seconds. and they were attributed then to 2 rings around the asteroid. So other telescopes, which also observed that event, could not do that. Another example is where for DFOS telescope, where you can see here is a high precision light curves of transiting planetary, transiting extrasolar planet systems. Which are very bright. Here's just one example that has been observed of one of these bright events on the southern hemisphere. And you could get the interesting is that these high precision for light curves were obtained also by defocusing the telescope. Together with the DFOS, and you could obtain better measurements and more improved measurements of the physical properties of such events. Now, coming to what's happening now. So now we have just recently, a few years ago, we are entering a second round of refurbishment. So that includes now the recommissioning of the spectroscopic part of the telescope, so that we can actually do spectroscopic observations with the Danish again. Last year, we also re-illuminized the mirror. And of course, with putting back a spectrograph, as easy as it sounds, right? It's never as easy in reality, really. So we also had to get up new calibration units, new hardware, new computers, and then of course you have to somehow match them with all the old stuff that's there. And so we here it's just a few people which are from the Danish side now largely involved in getting the software also up to speed and make it all compatible and working. Nice is if you're part of such a refurbishment process is that you actually get an opportunity to climb around the telescope. I've been here just mounting the calibration lamps. Not something you can do very often. So what can you do with a spectrograph in the end? Yeah, as I said, a spectrograph, you have different kinds of slits available. It's fairly similar as the IFOSC instrument at the Nordic Optical Telescope. It covers a wavelength range between 320 to 1000 nanometer, which is broadly covering also all the LSST filter bands. It's a low resolution spectrograph with, depending on what prism and slit you're choosing, you can vary the instrumental resolution. Given, of course, by the aperture, you're limited in the depth, how deep you can go. And if you want to take a spectra with a decent signal-to-noise ratio and a not too long observing time, and maybe half an hour, then you're sort of limited by about 18.5 magnitude. What's interesting, or what's really nice with the telescope is that over the last years, there has been a really super stable seeing conditions. That's also largely due to the construction of the dome in the telescope, which stays low at around 0.8, 0.9 arc seconds. So here I'm just, I've been digging out a few examples of type 1a spectra. They're probably one of the last ones before the decommissioning of the spectrograph taken. You can see the spectral quality of here are some examples of type 1a's at different phases, prior to peak, directly at peak, or even if you have a bright event, you even can observe it at late out to 250 days past peak. So given that, looking a bit now more into the future, what can the telescope be used for? And it can certainly tap into the potential of using as a new resource or as an additional resource for example, real-time spectroscopic identification of targets or multi-messenger candidate search. We also have plans for a dedicated spectroscopic survey of type 1a. I'm coming back to that in a second, hopefully. So what one question we also have been asking, as many of you obviously have been asking, is how can we find the targets that we actually most are interested in? How can we optimize our observations as much as possible? And to do so, we have been started out also developing a small prototype as a fast response alert system that can create a ranked target list that's also self-updating. So the main idea in this case is it's very designed just for the Danish right now. Is that we're listening, we're testing it, and we're listening to Think alerts. So thank you for all your efforts and CTF data, and also we're channeling right now Atlas data. and then put it through a filtering process where we compute a score for each of the targets that is based on the parameters that either for your science case or, of course, obviously for the Danish telescope, very specific. So we're also feeding in information like the weather conditions at the moment of observation or the whatever moon phase, what there is. So if you have a score for each of the targets, then you can rank all your targets, and the idea is to always have the top with the highest ranked target available when an observation ends, that you can right away start with the next most interesting target to observe. So some of this is still in the development, and our main developer is Aidan Sedgwick. He's a postdoc at DAC right now. And he also has some fun to, as it's obviously several others here have fun to do app. So we have developed a Slack bot right now. So we're using that also for testing and for monitoring targets from CDF that could be interesting for particular science cases. Also have done a Telegram if you don't like Slack, so you can watch that on the phone on multiple systems if you get bored sitting in the metro. And there, of course, ideas are to make in the future to develop a TOM toolkit plugin for maybe easier scheduling. This all is also in preparation for, as I mentioned before, for one of the surveys we have plans for to do. It's a spectroscopic survey of type 1a supernova with the primary goal to do spectroscopic standardization of supernova 1a's to really accurately measure dust extinction and distances out to the 1a's within a redshift limit of 0.08, which is simply given by the aperture of the telescope. So we can't go very much further. The concept is simple. We want to take spectra at peak or very, very close at peak together with photometry to have a really, really well spectrophotometrically calibrated spectra. We get host galaxy spectra once the supernova 1a has faded. And putting it all together with LSST, we expect that this will take about half an observing night. And then if we do this for 300 nights throughout the year, then we can actually build up a very, very large sample of type 1a, of really, really a uniform sample of a very well calibrated type 1a supernovae. And it has been shown also in the literature that taking spectroscopic information and the diversity into account in the standardization can really help to improve that part. So coming here at the end, just a quick summary. So the telescope is there. It's very stable. It's have been producing important results already in the past, and hope so will do so in the future. We hope that with all the refurbishment plans, we are going to be done and ready by LSST first light, so we can right away observe. And we think that it can be used as for programs that maybe can complement those of larger telescopes or other surveys. Some I've mentioned it, and of course, one thing also to say is that the telescope and all the refurbishment is right now, it's not part of any in-kind contribution. So the Danish in-kind contribution is to build the light independent data access center for LSST, where then also some of the data can be stored and processed. At this point, I would say the doors are open, so we are happy to and interested to coordinate the resources, the data, and also in future collaboration. So yeah, if you're interested, then just come and talk to us. And also, if you like, you can. It's nice to visit the Danish telescope. Thank you.
Thank you very much, Christa.